So let's talk about WebAssembly and why it matters to you as UI developers or front-end developers. How many of you are front-end developers? Okay, most of the crowd. That's okay. So maybe you're wondering, why do I have to attend a WebAssembly talk in my front-end development conference? Let's focus on JavaScript to begin with. Then I'm going to try to, I'm going to be speeding up and slowing down because
I love this topic, and maybe I start talking a lot about it. But what do you think makes JavaScript as a language so popular? Any ideas? I don't want to be the one talking at 9 a.m. in the morning all on my own. So, yeah, over there. Because it runs in the browser, that's right. And that's because it's high level, and you basically need nothing but a text editor and a browser, and you can run JavaScript. Of course, we have now bundlers and transpilers and ahead-of-time compilation for JavaScript and a lot of stuff in TypeScript. I don't know if Josh is here, he probably is not. But yeah, we have a lot of stuff that makes the, I don't know, the JavaScript ecosystem richer, right? I like to say that the JavaScript ecosystem is like the universe. Because, I don't know if you know, but the universe we live in, it keeps expanding and accelerating. That's the contrary of what we may assume, right? Something that expands starts slowing down, but JavaScript as an ecosystem starts, getting faster and faster and richer, and there are more frameworks, and there are more, tools, and so that attracts a very large crowd. We are 60 million JavaScript developers all over the world. That's the largest developer population in the world, over Python and other languages. And that's because the internet runs on JavaScript, right? You can have the backend on whatever language you want, but user interfaces are JavaScript, and we love it. Right? Do we love it? Do we love JavaScript? Yeah, we love JavaScript. But we love it because it's high level, because it's accessible. One could say it's easy to learn. That's if you understand how to concatenate strings and what's going to happen if you do it with numbers. But yeah, anyway, it's relatively accessible to everyone. And that makes it attractive. And that's why we have such a large JavaScript developer population. But the fact that it's high level, and because of that, again, I have some stats. 63% of developers have admitted to have coded JavaScript over their developer lifetime, as opposed to 49% Python. It has some cons or some drawbacks that we're going to discuss later. And you may be wondering why she cares so much about these statistics. I am going to very briefly introduce myself. I do because I work in developer tools and experiences for JavaScript developers, and I want to make sure that we always have the best developer tools available to run our applications, and that we can focus on our user interfaces and not so much on the whatever accessories to the runtime to make it work. But yeah, let's explore how it works, and then we can decide if there are some things that could be made better. Made better is not probably the right way to put it, but when we write a JavaScript script and then we run it in the browser, what happens is this. We have the script, then the parser grabs that script, and it does some lexical parsing, by the way, and it outputs this thing that is called the abstract syntax tree, which is like a hierarchy of nodes, and then from that, the interpreter compiles it to bytecode, which is a high-level binary that is not very optimal, and then the compiler grabs that bytecode and turns it into optimal machine code that can be run at a lower level. Because at a lower level, we have higher performance. And again, we don't need to pre-compile our JavaScript. We can type it and send it to the browser, and then the browser, the JavaScript engine, will do all this work. But there's still work done, of course, because machines read only binary, and what we write is very, very high level. What are those JavaScript engines? You probably are very familiar with V8, Chrome, Chromium. Also, maybe you've heard of SpiderMonkey. SpiderMonkey is the analog to V8, but for Mozilla browsers. There are more. And those are the tools responsible for taking your script, your JavaScript, into that flow, and so you can get the binary code. And again, it's important to know this because at a lower level, where this binary code runs, we have higher performance, right? Closer to the metal, let's say, everything runs faster than it does at a higher level. And why performance matters to JavaScript developers? Well, I don't have to tell you this probably because you are UI experts and you're probably very familiar with UX studies, and you know that the attention span of users has dropped, or yeah, has dropped dramatically, I would say, to 8 seconds. It's like, it's incredible. Just 8 seconds to catch somebody's attention and prevent bounce rate in any application. Did you consider what 8 seconds are? That's it. Have you seen that? Look at it again. That's it. If you didn't make your UI interactive, so if you don't have a short time to interactive, if you are not compliant with all those core web vitals or whatever metrics, you're in trouble, right? And your customers are in trouble because end users will just abandon an experience out of not getting what they want. They're used to TikTok and all these very fast interactions, and now having to wait for something to happen, that doesn't cut it anymore. So yeah, JavaScript has been around for 27 years. I don't know if you knew this, but that's the age of our beloved language. But the expectations of the end users have really evolved over time, and we need higher and higher performance every time. And yeah, I don't have to tell you this, but with the emergence and success of many libraries and frameworks in the early, or I would say late 2000s, like AngularJS, Ember, Backbone, jQuery, all those things that were really, really popular back in the, I don't know, 2010, let's say, everything was happening client-side. And everything has been happening client-side for a very long time. But client-side, it's a very uncharted territory because we don't know exactly what's the capacity of an end-user machine, or what browser they're using, or what's their connection speed. And whatever is happening client-side is affected, or the performance of it is affected by all those parameters that we cannot control, right? Luckily, not long ago, for a few years, but I would say 3 to 2 years, we have seen the emergence of meta frameworks. Are you familiar with meta frameworks? Yes? Can you say what a meta framework is? Next, for example, yes. So these are frameworks that are built on top of other frameworks, hence meta. right? And they have additional capabilities, or they enable additional capabilities to a framework. So React, for example, used to be all client-side. Now it is moving to a server-side strategy. But there are frameworks that were built with this architecture and design in mind. One of them is Next.js, Astro, 11t, I don't know. There are many of them. And that's a good thing, because many of the workloads that were happening in JavaScript, client-side, in the main thread, that were slowing things down and impacting performance are now back to the server, right? And that's efficient. Server-side rendering happens typically on demand. So you hit a URL, and something happens that the HTML gets rendered, it gets cached, and it gets served. And with these meta frameworks also, we can do composition. So sometimes we pass a header or rules or a cookie or whatever, and then we fetch a snippet of HTML from one backend, another one from another one. We fetch data. We grab that statically rendered page, and we hydrate it, which means we make it dynamic again. Are you all familiar with these techniques? Are you using these kind of techniques when you are designing your UIs? Are you considering all these new strategies of rendering? Come on, people. Yeah. Yes, of course, we are. Because why? Because we want to be fast. We want to be performant. We want to deliver experiences that users enjoy and they don't want to abandon. And this we do with the use of, for example, composable micro-frontends. In the local stack, we combine sometimes, like we said, we have some static page that comes back from the render, from the server, sorry, and then we bootstrap JavaScript selectively to certain areas of the page or components that are more dynamic, and then we infer state, and this makes the experience dynamic again. And there is another way to do this. And yeah, you were saying, like, wasn't this a talk about WebAssembly, and now she's talking about JavaScript? But WebAssembly runs like JavaScript in the JavaScript engine, right? And we can use it to build these dynamic experiences. And I think that as front-end developers, it's very, very good to know the possibilities so we can decide what we're going to run in our main thread and what we may defer to different workers or runtimes or context of execution. So what I'm going to do is I'm going to show you a use case. We discussed Astro before. This is this is one of the templates they have, Starlight, and it's something that is offered to build documentation sites, mostly. And the interesting part is that this is like any Astro site. It's statically generated at build time. So the engine grabs all these pages that we code and generates HTML and caches it. But this search capability, let me bring the developer tools over here. So, no, maybe let me do it the other way around. This is going to happen here. So if we go to sources, we see that it's fetching a lot of stuff like bundles and CSS from the CDN. But if I use this search component, boom, suddenly I have this WebAssembly running. And why are we running this search capability in WebAssembly? Because that allows us to have most of the site static, super fast, render in nanoseconds, and also have a runtime that very efficiently and low level will ingest all this HTML and index it and allow you to have a search capability with very, very minimal use of client-side resources. All this happens client-side. And it's really amazing. So we are already seeing the use of WebAssembly mixed with JavaScript in meta frameworks in a very, very efficient way. Now, this is not JavaScript compiled to WebAssembly. This is called, let me go back. This is called page find, and it's actually built with Rust and compiled to WebAssembly. And yeah, it provides a real optimal search API for this type of websites. Were you familiar with page find? Did you know that it ran in WebAssembly? Okay. So what is WebAssembly? It's, for those that don't know, it's a binary instructions format. It's not a language. It's a compiling target. That means that you write the code in your preferred language as long as it has a tool chain that allows you to compile to Wasm as target, then you're good to go. That's C, C++, Rust, obviously. But there are also tool chains in the making. They're not fully stable for TypeScript, JavaScript. So the good thing about WebAssembly is a web platform standard, which means that all the APIs are a standard for the internet, and there is a W3C group that is working on the standardization of all these APIs. And basically, it provides a lot of advantages that we're going to be discussing later. What happens with WebAssembly is you have your code, your program, your script. You pass it through the tool chain, and that compiles to Wasm as target, and then you can import it back to your JavaScript program, which is what we just saw. So WebAssembly doesn't really have, except for the JavaScript bindings API, it doesn't really have any additional APIs. What it does is it offers a system of imports and exports. And what we do is, for example, if we see the code above, that's WebAssembly text format, which I don't recommend anybody learns because it's really confusing. But what it does over here is, if you see, it imports an environment and a function that is print line, and then it basically also exports a hello world function that is going to be then imported to, let's see the JavaScript that is running side to side with this. You can map this this example to what we saw earlier with page find, right? So we do a fetch for the WebAssembly module, and then we get an array buffer, which is the bytes. And those bytes, we're going to use the WebAssembly API to compile and to instantiate a new WebAssembly module. And from that instantiation, then we're going to grab that environment that we saw was imported over here, right? And that will allow us use the print line function mapped to the JavaScript console log as a binding. And that's it. We export the hello world over here, and then we can use it directly in our JavaScript. That's not as straightforward as it looks, obviously, but you can try it. If you go to WebAssembly Mozilla, there are some tools like What to Wasm that you can that allows you to experiment and play around with WebAssembly. Now, again, why does this matter to you as a user interface developer? What do you think? what possibilities does this open to you? One of them is portability. So parity between execution contexts. And you're going to be thinking, why? I mean, it's just running in the browser. That doesn't expand anything. That doesn't give me any portability over JavaScript. But you know that there are user interfaces right now everywhere. Like JavaScript is literally running even in light bulbs today. And by the way, it runs everywhere. And this is completely out of topic, but this is something I came across in a plane, and I was a little bit concerned, and I made a photo. Can you spot why I was concerned? So this is JavaScript, right? I was wondering if the rest of the systems were also undefined, but yeah, I landed, so I guess not. Yeah. Anyway, I digress. So, why does it matter to us as user interface developers? We write our JavaScript, and maybe there is this opportunity that this JavaScript we are writing, we want to run somewhere else that is not a browser, because we want to reduce maintenance. We don't want to write programs 20 times in different languages and have to maintain different programs, right? So how could we potentially do this? Well, we can with Wasm, that is enabled with what is called the WebAssembly system interface. So what the WebAssembly system interface does is it infers, or it adds additional access to other interfaces that are of the system, or that we decide the host may want to provide to this WebAssembly module, so it can run somewhere else that is not the browser, as though it was in the browser. And then we can import it to our JavaScript, just like we saw before. So again, the WebAssembly system interface, or WASI. You may have heard about WASI, and WASI enabled Wasm. It's a modular system, and again, it was designed to be working outside of any browser. It's fully compliant with POSIX systems, which means it has some in-out file system interfaces and other things that work at a very, very low level in operating systems. And it runs in specific runtimes, like, for example, Wasm time, right? So it's, again, the same binary target, but then you're going to be enabling or making available additional interfaces for that WebAssembly module to run. That's one of the the concepts that enables isomorphism. That is very important for us as JavaScript developers. So we can run, for example, our same JavaScript code from backend to frontend, and that's also one of the concepts behind the meta frameworks. And additionally, we can think of trisomorphism. Trisomorphism allows us to run code even in workers outside of the main thread of JavaScript, like a web worker, for example. So let's see a little demo I have, so I can show you this. Let me get it over here. So this is in GitHub. I forgot to make it public, but I will today. It's just a little JavaScript program that has a function that turns any word to binary data, or to its binary representation. And so it takes an input, and it handles a click, obviously, here, and it writes an output. And I have compiled it with Vite. So it's just a regular JavaScript. If you see over here, Let me open here, sorry. So if you see over here, I have a backup just in case something didn't work. But this is the file, this BitTranslate, right? And I just have it running here with Bit, like I mentioned. Where is the, I don't know if this is the, no, this is the slides, localhost. Okay, so I just enter, I don't know, web, and I go binary and just the representation of it. Right, that's nothing very impressive, right? But what if you just have to open your mind to the possibilities here? What if I go and grab my tool chain, which in this case is Javi? It's a tool chain for WebAssembly to run somewhere else, not in the browser, that is designed by the Shopify team. So I go to my console, and let's not spoil it. So basically, I have it installed. I have Java installed. I have Wasm time installed in my machine, this alternative runtime that is not the browser. And so I go, and I want to do this side to side. So give me a moment to move it together with the VS Code thing. So I just run it. And you're going to see on the side, it's going to, boom, compile. I don't know if you ever saw Wasm compilation, but before I was working with WebAssembly, I was thinking that maybe it takes a very long time, because I was a Java developer back in the day, and I remember them maybe going, trying to compile things. But this is very, very fast. And so I have the Wasm module over here. This is preview 1. In preview 1 of the WASI, the WebAssembly system interface, we're talking about modules. In the preview 2, they are moving to a component model, which is going to be even more intuitive for JavaScript developers. But now, if I want to run it, I can go and say echo web, right? And I tell Wasm time to run this binary translate. And boom, it gives me exactly the same result, because it's running exactly the same JavaScript code. There is no difference. The only thing that you see is that here if you take a deeper look, you see I have some conditionals, and I tell my JavaScript, okay, if you're running in JavaScript in the browser, in the JavaScript engine, just use the regular input-output interfaces of the system. If you are in Wasm time or somewhere outside of the browser, in this case, use Javi I/O operations, write sync, or output operations over here. Where is my Javi? Over here. If type Javi is defined, well, then run it, read it, or read the buffer with Javi. And that's it. So you are writing one code, one script, and you're running it in the browser or outside of the browser with whatever interface is available. So let's go back to the presentation. I think it's this one, but I no longer have it full. But it's okay, I guess. So basically, when we're running this type of modules that are enabled with WASI, if we want to do it in the browser, it's also possible, but we need to use what is called a browser shim that makes all those interfaces also, those interfaces I'm talking about, the DOM, about the network, all those things are not available out of the box to Wasm or WASI. That's one of the things that makes Wasm so secure, that you are the one deciding what interfaces of the host are available to your program. And you can, for example, interoperate from the worker to the window and so on, using regular JavaScript interfaces like post message. You send a message to the, from your worker to your main program in JavaScript just by posting it with window post message. So imagine the possibilities that enables in the cloud, right? If you are in, in a worker, in a Cloudflare worker, or anywhere on the edge, you're running some very low-level Wasm code and interacting with an application, interoperating, and making it super fast, so you can also offer the same kind of immediate experiences to your end users just by connecting these two runtimes and letting Wasm do the hard work, do the heavy compute, because it does it much faster by running much closer to the bare metal. In terms of security, WebAssembly is super secure because, like I mentioned, it's sandboxed. Anything that it has access to is because you made it have access to. And you can also control the memory. The memory is what is called memory safe, because you decide what memory is going to be allocated and available to it. So it's linear, and there cannot be memory exploits, which is one of the most, let's say, worrisome vulnerabilities when running code on the web. And that opens, of course, a myriad of opportunities to run the same code in the browser, also in systems that are very critical, like, medical systems. Because we design user interfaces not only for the web, right? But for systems that are, taking care of the life of people, or doing banking systems, or things that really need to be very, very encapsulated and safe. Trade-offs, of course. Everything has trade-offs. There are more layers to debug if you're working or running code in different workers or systems or runtimes. You obviously, if you have a problem, a bug, you're going to have to go through many different layers to figure it out. Standards are in preview, like I mentioned before, so they're not very stable. Sometimes they change, and they change because they're not efficient enough, and the people working behind these technologies, they decide to change them. And the tool chains are not available for every language. So some languages, there are a lot of languages that already have tool chains to compile to Wasm, but not all of them. So if you're I don't remember right now. If you're a Java developer, I think you don't have so much luck yet. But this is all. I didn't see where we are in time. We still have time? Oh, 10 minutes. OK. But I think I said everything I wanted to say. I invite you to visit a website I authored not long ago. I speak about micro front-end technologies, about all these new rendering strategies, from setup to interfaces design, to APIs design, to operations. I try to cover it all for front-end developers. So yeah, give it a look. And those are the QR codes to explore more and learn more. And that's it. Thank you very much.